Are we on? Yes, we are on. We are ready. We are rocking and rolling. Okay, let's go over some of the stuff that's on the board. Now, this is why I added to the material. Now, the first section in the chapter on states of matter is about gases, correct? And the second section is about liquids. Clear? And the fourth section is about phase change. Correct? Now, when I say to you, let's learn about gases and liquids, it's really, we're going to learn about the nature of those things. And it's more than just the nature of gases and liquids like you learned in the middle school. It's also the nature of fluids. A gas or a liquid, they're fluids because they can flow. So the fact that they have that nature consistent between the two is also very significant. Water is kind of a neat substance because within a very, very small range of temperatures, relative to what some substances, the range of temperature for other substances relative to the three phases, water is a very narrow range. You know, you could get below zero and it's a solid. You can have water vapor in the air, really at any temperature. You've felt humidity, right? You've felt that. Here in this country, it's especially significant in the summer, the humidity, because it gets so hot. It's 45, 46, 47 degrees Celsius. We all boil water. We all make tea, coffee. You use it in cooking. So within a very small range of temperatures, we have all these different phases of water. Yes? So it's kind of a neat substance. So we're going to look at that on the board. What happens if I heat solid ice at negative 20 degrees Celsius? I heat it. I'm going to heat ice at negative 20 degrees Celsius, and I'm going to melt it, and then I'm going to heat the liquid water as a result of the melting, and then we're going to boil it, and then we're going to convert it to the gaseous form. What do you call a gaseous form of water? Vapor. When you think of really hot vapor, hot water vapor, you call it what?
Steam.
Steam, like really hot. Okay. And why does steam at 100 degrees Celsius, can water be a gas at 100 degrees Celsius? Sure, it can finish boiling, right? So like 100 and just a pinch, or 100 and just a little water, right? So within 100 degrees, you can have water. You can have, this is water as a liquid, right? This is water as a gas, correct? This is steam. So why is steam over here can burn so much more thoroughly? These are much worse burns over here than over here. Well, you see this? We're not going to spend a lot of time on this chart. There's a few things I want to show you. I think it's a significant chart to show you, considering we're doing phase change. Make sense? Reasonable? As long as I don't get too technical. Haley, you think that's reasonable? Yeah, that's all right, okay? Yeah, I'm not going to get too technical, but I want to show you a few things. Okay? All right, now. Excuse me. Here is a solid. Very tightly packed together molecules in a solid, right? Very tightly packed together, correct? And they vibrate and do all kinds of weird things. And if they're a crystal, they're going to be like an ionic crystal or a covalent. They're going to be a lot of vibrating, not a lot of movement there because they're kind of locked in a crystalline form, but there's going to be a lot of movement, a lot of vibrational energy, right? Yes? Okay. And then you're going to have water. let's say water's up here. Okay, where the water's going to be farther apart and that it can move and collide, right? And there's a certain range where it's staying pretty much the same distance, water. The density of water is very similar at 100 degrees Celsius as it is at 0 degrees Celsius. Yeah, it's different densities, but they're very similar depending on the precision you're looking for, correct? So you would say that the average distance between water molecules pretty significantly the same, correct? Yes. And then you have gases, you know, a gas, which is, I don't know, is this coming out, like if I go like this?
Yeah.
And then like down here, you know, and over here, and up here, right? So gases are very far apart. It can get even farther apart. It's kind of unlimited, isn't it? Yeah, a gas, yes. Okay, so now you don't really know what that means, correct? Other than you know what distances are. Does that make sense to you?
Yeah.
That a solid would be closer, a liquid would be a little farther, and gas would be farther. Does that make sense? So that makes sense, right? Does it also make sense that those molecules move? Kinetic theory of gases, kinetic theories, right? So that makes sense to you, right? All right. As a result of the movement, they collide, right? And the hotter it is, the more they collide. Makes sense, right? Collisions, right? And what's temperature? Temperature is just a measurement of collisions, right? Kind of the same as pressure. The more collisions, the greater the pressure too, right? So there's a similarity there, isn't there? And in the next chapter, we're going to look at the similarity. We're going to look at a relationship between pressure and temperature. It's called Gay-Lussac's law. Very famous person in the study of gas laws. So the fact that these are close together, these are farther apart, that makes sense. They're moving, right? And the fact that these stay within a certain limited range, and you just increase the number of collisions, right? It makes sense, right? Yes? So there's a certain kinetic energy. The more kinetic energy, the more collisions. That makes sense to you, right? Now, but how do they change the distance? That's what you don't know, right? How do you go from close together to farther apart?
They repel.
Well, yeah, all right, but how do you do that? All right, look, guys. You remember middle school science, right? Kinetic energy, energy of motion, right? What's potential energy?
And it could go into motion.
Energy of what?
Displacement.
Energy of displacement, energy of
Gravity. Speed.
gravity, maybe. Energy of position, right? Right? The farther off the ground, right? It's down here. Am I increasing or decreasing the potential energy? You ready? I'm increasing it, right? So as you're going from here to here, what are you doing to the potential energy? What are you doing? You're increasing it. Well, how do you increase the potential energy? If I increase the potential energy, am I increasing the kinetic energy?
Yeah.
No. Look, you ready? That's a potential energy, right? Right? Snapshot. Right? Potential energy. We'll say that's potential energy A, right? Snapshot. Okay? That's B. That's a new potential energy. Snapshot. So now let's compare the two pictures. Picture 1, picture 2. What has a higher potential energy, A or B? B. Did I increase the kinetic energy? No, I just increased the potential energy, right?
So just the place where it is.
Yeah, exactly, the place where it is. Exactly. That has a certain energy. I want to increase the potential energy, I have that, right? I will increase the potential energy, now you have that, right? Right? Yes or no?
Yes.
Okay, good. Well, how do I increase the potential energy without the kinetic energy increasing? That's a question. How do I increase the potential energy without the kinetic energy increasing. Let me just say something about kinetic energy again. Kinetic energy is the energy of motion, right? Energy of motion. You have motion, you have collisions. You have collisions, you have temperature, right? So you have increased kinetic energy, you're going to have increased temperature, right? So how do you know you're not increasing the kinetic energy? What's a very easy way of saying it? There's no temperature change, right? Is that good? Fair? Okay. Is there any place on this graph where in the passage of time, is there any place on this graph, look carefully, chartreuse lady, look carefully, is there any place on this graph where in the passage of time there is no change in kinetic energy? There's no change in temperature. Anybody can spot it? Where? He's pointing to a wall. Let the record show. He's pointing to a wall. That makes a lot of sense. Okay. He pointed to the wall. Can you give me some nouns?
Where it says 8 calories per gram.
Where it says 80 calories per gram. And 540 calories per gram. Is that what you're pointing to? So in other words, will the jury understand that the defendant is, the witness is saying, is pointing to this horizontal line. The witness is pointing to the horizontal line above which says 80 calories per gram and the horizontal line that says 540 calories per gram. Is that correct, witness?
Yes.
Excellent. Good. Now, so what does that mean, 80 calories? When you think of 80 calories, what do you think of?
Food.
You think of energy, right? Yeah, and it is. It's energy. We're not going to get into it, but it's energy. When you think of calories, what do you think of? You think of energy, right? Okay? Anybody not think of energy? You don't think of energy? What do you think of?
Food.
You think of food. Okay. He thinks of food. Okay. Okay. He thinks of food. Okay. Well, this is called H for heat, F for fusion. 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 In other words, when I go from a liquid to a gas, I take out the heat of fusion and I form a solid. This heat of fusion, this is a potential energy. That's what that is. It's a potential energy. This is also a potential energy. You know what that's called? This is called heat of vaporization. Heat of vaporization. It's a potential energy. Make sense? Okay, now look at this. But isn't the material though, once it goes in, it's got more heat content, doesn't it? Doesn't it? It's got more heat content. Yes or no? Burns. Look at the burn. A burn here versus a burn here. Which one's going to be worse? Before or after you put in 540? After, yeah. 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 Now, what has a greater change in potential energy? Liquid to gas or solid to liquid? Liquid to gas. What is 540 divided by 80? About 7-ish. 6.5, whatever. Somebody do it. 540 divided by 80. 6.7. Okay? So it's significant, isn't it? Does that make sense to you? When you think of ice and water, there's really not much of a change between the distance between the molecules, are there? right? I can see ice, right? I can see water, right? Can you see humidity? Can you see it? No, it's so far apart, I can't see it. Do you see that? You understand? Does that make sense? Yes? So the fact that water has these properties, don't you think it may be significant? As long as we don't get crazy, let's not go crazy. Do you understand what I said so far? Yeah, as long as I don't go crazy, that's really it. It's reasonable to talk about that because water is very important. Our entire weather systems, has anybody ever been near a hurricane? Where does it get that energy? It gets it from the sun shining on the ocean. When does the hurricane peter out? When it goes over land. When it goes into colder water up north. They kind of die. Yeah? All right. Let's also look at a few other things. Let's look at a few other things. Let's look at these over here. It says cooling process. Okay? Cooling process. Let's talk about this. Snow. Anybody ever seen snow before? Okay, you've seen snow. Okay. Has anybody ever seen a pile of snow melting in a parking lot? It takes forever. Has anybody ever seen it? You've never seen it? How many people have never seen it? Raise your hand. It's amazing. I have half the class raising their hand. That's amazing to me. I love it. No, I love it. I love it. Absolutely love it. No, you don't have to apologize. I just love it. I think it's cool. Okay? All right, so when ice is melting in a parking lot, what's it going from? What's the change? Solid to liquid, okay? So what's the snow absorbing? It's absorbing heat. Do you get that? Okay, now, this is important. This is important. Listen carefully. Cooling process, heating process. It's going to be all over your test. It's fair. And I'm going to show you why. If you're not from planet Earth, it may not be fair. But if you're from planet Earth, they're fair questions. Okay? Let me show you why. When you talk about a cooling process or a heating process, it's relative to the environment. What's happening to the environment? Okay? So now we have two things. We have snow melting, and we have the effect of that on the environment. Okay? What does snow need to melt? It needs what? It needs heat. Where's it getting it from? No.
From the air around it.
Well, the sun, but the environment, the air around it, right? Correct? So what's happening to the air around the snow? Is it becoming warmer or colder?
Warmer. Colder.
No, wait, now you guys aren't thinking. See? You're taking this for granted. Now, this is like a test. Like the Men in Black give these tests to whether or not you're an alien, and then they deport you to whatever planet, right? You're from planet Earth, right? Okay, good. Let's try this again. Okay. The snow needs energy to melt, right? Well, where's it getting the energy from? From the air. Let's say there's no sun out. It's getting from the air, right? The air's warmer than the snow, true or false? I'm walking around with a light jacket on. It's not freezing, right? All right. So where's the snow getting the energy to melt? It's getting from the environment, right? Okay. Well, what's happening to the environment if the snow is absorbing energy? What's happening to the environment around the ice and snow? Is it becoming cooler or warmer?
Colder.
How can it be getting warmer if you're taking energy away from the environment? What's happening to the environment? Martha? All right, don't go crazy now. All right, that was a little crazy. But that was good, though. You're right. She's absolutely right. It's an endothermic reaction. You sounded very scientific. I like that. I like that a lot. Go Pumas. Pumas! All right. They have no idea. If somebody's looking at this from Canada, they're going like, what is a Puma? He's teaching a class full of Pumas. No, not that. Okay, so This is your body, right? If your body loses heat, what does that feel like? That's the definition of cold. It's a sensation that's defined by the human body. How many people are sometimes cold in their house? But yet somebody in the same family is hot. Does that make any sense to you? It's like weird. You want to just beat up your younger brother, right?
Yes.
Turn that air conditioning. Turn down the air conditioning. What does that mean? Does that mean make it colder or make it hotter? What does it mean? How many people are confused when you say turn down the air conditioning and you're not sure if that means get it colder or hotter or turn down the, what do you, I'm cold! Okay? Now, so do you see this? Your body loses energy, right? It's going to be cold. If your body gains energy, it's going to be hot, right? Yes? All right. This is the environment, right? This is your body. This is the environment. We're talking about the environment, okay? For a second. I want to talk about the environment. Are you ready? You ready? We're talking about, what's diffusion? Anna. Oh my God. No, not that. Diffusion. Don't call on me and ask me such a weird question. Is that what you're saying? What's diffusion? Martha, do you want to give us a scientific explanation of diffusion?
The spontaneous
Flow. I like that. She used the word that I don't think I use maybe 5 times in my life. That was really quite amazing. Go ahead. What else? It's spontaneous.
spontaneous dispersion of gas molecules.
It's a spontaneous dispersion of gas. God, this is like, are you like human or something? Or, I mean, she sounded incredibly intelligent. Excellent. It's like a spontaneous something, right? Well, it's a flow. It's a flow. It's spontaneous, I guess you could say, from high concentration, low concentration. If I open up a bottle of ammonia, right? Ammonia water, if you want to be technical, and I open it up, what are you going to smell? You're going to smell ammonia, right? It's going to diffuse, right? If I light a fire up here, what's going to happen to the heat? It's going to start to diffuse to the back, right?
Yeah.
Yes, right? Okay. So diffusion is a flow of matter or energy. This is important. Big. You ready? Diffusion is a flow of matter or energy from a region of high concentration to a region of low concentration. Is that okay? I got to check with my producer, Martha. Martha, is that all right? Right? Martha is our technical producer. She's the technical consultant. Okay? Yeah, she sounds like an encyclopedia. Okay? Yes?
Is diffusion also like spraying like a perfume or something else?
Same thing.
Same thing?
The TJ's, he's experimenting with perfumes. TJ, no, that's all right. Yeah, men call it cologne though, you know what I mean? You got to use a deep voice. Yeah, we don't use perfumes, we use cologne, right? Same thing. Trust me, it's the same thing. Okay, so I used to love to steal my daughter's perfumes. They smell great. You know, they used to drive, and I said, you have perfume on? No, I have cologne on, you know. Deep voice, I have cologne on. So yes, it's the same thing. It's a dispersion. It's a flow of matter or energy from a region of high concentration to a region of low concentration. Make sense? Same thing here. What happens if it's really cold outside? Where's the flow of energy going to be? The flow of energy is going to be from a region of high concentration, your body, right, to a region of low concentration, the environment, and you're going to feel cold, right? Yes or no? Yeah. If we're in Abu Dhabi in late July, where it's like 10 degrees above body temperature, what does it feel like when you go outside? It feels like an oven. Yeah? You thought ovens were tough like at home, you know, where, oh, I'm in New Jersey, I know what it feels like to be hot. You'd have no concept. Breathing is difficult. It's really awful. People leave, you know? It's unbelievable it's unbelievable. So you're going to go, it's going to feel hot because the environment is high energy, region of high concentration in the environment, region of low concentration in your body. Now the flow is in. I take my hand and I put it in fire, right? Yes? And I get some nice steak sauce, yeah? Yeah, a little salt and pepper, yeah? Tastes great, doesn't it? Nice cooked. Yeah? I'll take my hand medium, thank you. Okay? Right? Little steak sauce on the side. Dip it. Some nice bread. It's the best. Okay? Well, that's region of high concentration. The environment to region of low concentration, your hand, so it's going to cook. Right? Now, you're out in the top of Mount Everest, and you lose your mind and you take all of your coats off. And you're there in your underwear. Okay? What's going to happen? You're going to freeze. They're going to call you popsicle. Okay? They're going to call you frozen. Okay? Okay? And because region of low concentration here. What is the difference between frostbite, where a piece of your hand freezes, piece of your finger, I had it. I didn't lose any, I'm fine. But when I was getting frostbite, it is so painful. It is so painful. Did you ever put your hands underwater and you don't realize, oh my God, it's on full blast hot. And there's like that split second where it doesn't hurt yet, but you know it's going to hurt a lot. And you're just waiting for this wave of pain to come across your skin, and you're like, ow! And that feeling of burning. You've done that, right? Yeah, okay. What, that feeling, right? Yeah, that burning feeling? All right, fine, you're fine, okay, everything's fine. What's the difference between that and playing in the snow without gloves to the point where your hand starts to freeze and it gets really painful? What's the difference between that and putting your hand in boiling hot water? Absolutely nothing. They're both burns. What is a burn? What is a burn? Define for me the word burn. Irritation. Okay. Okay. Abdullah, you are a burn. No, I'm teasing you. I'm teasing you. That was a low shot. No, I'm not talking about your height. Okay. Oh, that's another one. Oh my God. Okay. Sorry, big guy. Sorry, big guy. I'm sorry. Sorry. I know I'm being filmed. I actually have to behave myself. Okay. I have a couple other ones that are coming in. Okay. So what's the difference? Absolutely nothing. What's a burn? Abdullah? Oh, there's a smile. Okay. Fatima? Are you ready? You ready? Dehydration. That's all it is. Do you ever take beef or chicken out of the freezer and there's a little piece of the wrapper broken and it's kind of dried out looking? That's a burn. It's freezer burn. It's a burn. It's a piece of dehydration. What happens? When it dehydrates, the tissue dies. Right? That's what a burn is. It's the death of tissue through dehydration. Now, when you think of a burn, you think of what? Putting your hand in fire, letting it cook, the steak sauce, the salt and pepper, right? Maybe some Middle Eastern ingredients. We want to stay local, okay? Right? What are some nice spices around here? Saffron? Do you use saffron around here?
Yeah, a lot.
A lot of saffron. Okay, so saffron, right? So when you think of a burn, you think of like cooking a hamburger. It's burned, but it's not real burned. I can eat it. It's just perfect. But isn't that burning? Isn't that the dehydration of the tissue? When you cook chicken, don't you have burned flesh, burned protein? Isn't that what you're eating? Can you imagine if you did that to your own skin? Would that feel, oh, that's really good. Give me some steak sauce. I'll eat that.
Why not?
No, of course you're not going to. That's what you're doing. When you turn your nose up because your food is burned, that's not just burned. You're converting it to carbon. It's not burned. It's carbonized. When you burn something, you're dehydrating it. That's a burn. I'm not talking about undergoing a complete and utter chemical reaction where you're producing carbon. Right? You get it? Okay. So, cooling process, heating process, you got to know what you're talking about. When I talk about a cooling process or heating process relative to hot and cold, what is it relative to? The body, right? Right? It's relative to the body, right? When I feel cold, it's relative to the body, right? When I feel hot, it's relative to the body. Correct? Now think about this. Now here's your question. You ready? I go outside and I don't have enough clothes on and it's like snowing out. What's happening to the heat inside of my body? Is it leaving or am I getting even more energy? What's happening? It's leaving. Okay, here you go. You ready? All right, now. Relative to the environment, Abdullah, are you heating the environment or cooling the environment with the heat of your body if you go outside and it's cold? Yeah, very good. Excellent. You're heating the environment, aren't you? You're heating the environment with your body heat. Yes? So now, relative to the environment, Abdullah, hang on there, pay attention, focus. Relative to the environment, is it a cooling process or a heating process? Relative to the environment.
Heating.
Yes! It's a heating process. All right, let's go back to the snow. Okay? All right? What does the snow need to melt? What does it need? It needs what? It needs energy, right? Right? Okay? Now the snow is your body, right? The snow is your body, right? But we're talking about relative to the environment, not relative to your body or the snow, right? So the ice is getting energy to melt, right? Where's it getting it from? The environment. Okay, good. So the environment, is the environment losing heat or gaining heat? It's losing heat. Okay, good. Ice melting, a pile of snow melting. You ready, Abdullah? This is it. We've just spent 20 minutes on this. Yes or no, freezing. You can do this. You ready? Little pressure, huh? Little pressure. Okay, here we go. Take your time. Okay. You ready? Take your time. Nobody help them. All right, you ready? Okay. Snow melting in a parking lot. Okay, it's melting. Relative to the environment. Is that a cooling process or a heating process? Take your time. Shall we play some Jeopardy music? Da 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 da.
No, it's cooling.
Cooling process. Yes, it's a cooling process. Excellent, excellent, excellent. Now, let's do another one. Let's do another one. Let's do another one. Let's do another one. All right, now you're taking a shower. Shower's off. A lot of steam all over the place. You get out of the shower. What does it feel like? What does it feel like? It feels cold, right? When you get out of the shower, you take it. You're a mess today, okay? I want you to know that, okay? You're a mess. You get out of the shower. The shower curtain, you leave it in place, but you get out of the shower, and it's chilly, right? Right? You get right back in the shower. Well, what's happening in the shower? What do you see in the shower? Steam, right? Isn't that, and what's the steam? What is steam? No, you don't see steam. What do you see? You don't see steam. You see steam condensing, right?
Yeah.
Right? You can't see steam. What's that white stuff? That's condensing. That's steam that's condensing. Do you get it? You get it? Steam is invisible. That's invisible. That's invisible. This is what you see. It's condensing to water vapor. This is what you see. See that? You see that, right? But what's happening, so you go back in the shower, right? Because the steam is condensing. If the steam is condensing, what is it giving off? If the steam is condensing, what is it giving off? Energy. You see that? It's giving off energy. But I thought I said that it wasn't kinetic energy. But it's energy, right? It's giving off now. When you heated that water and the water stayed the same, aren't you heating it though? You're still heating it. You're still putting flame into that water, aren't you? You're still gaining energy. Well, that energy comes back out, man. It's hot. 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 Right? Yes or no? Right? That flame is going in there. It's staying a plateau, but that flame is going in there. Rhoda, we're filming. How may I help you?
I need my brother because he's getting so.
You need your brother? Sultan? I don't know. Why don't you go outside and have a meeting? That would be a good start. Okay, excellent. Okay, so what is the steam giving off in the shower? It's giving off energy. So when you go back when you go in the shower, what does it feel like? What does it feel like? Hey, look, if the steam is giving off energy, it's like a little furnace in there. That steam is giving energy back to the environment. You're the environment. So what do you feel? You feel heat. It's warmer, isn't it? Isn't it warmer in the shower than outside the shower? I go back in the shower. Right? The steam is giving off heat. I'm getting the heat. I want heat. Right? Yes or no? I'm asking you a question. Martha, how are we doing? How am I doing, all right? I had to check with my producer every once in a while. Okay, good. All right, good. So we looked at cooling process, heating process, burns, surface area. What does that mean? Surface area. I have an ice cube. I'm going to take an ice cube and melt it. Cube. Now instead, I'm going to take a second ice cube and I'm going to crunch it up. What's going to melt faster, the crunched up ice cube or the solid ice cube? The crunched up one. Why? Surface area, right? Why am I talking about surface area? When we do kinetics and we do experimenting and we do solutions, surface area is a critical factor in chemical reactions. Critical. Understand? Okay. All right. Snow, shower, fire. Hey, did anybody ever see people walking on coals? You know, how does that work? I'm going to tell you. I'm going to give away the secret. But how does it work? Could you? Is it a mental thing? What is it? How does it work? How does it work?
Don't you have to like put less of the surface area?
Nope. Does water conduct heat well? I'm asking you a question. Does water conduct heat? Yeah, a little bit, not bad. It's pretty terrible. Do you know, I could take a test tube with test tube holder, right? It would look like this. I could take a test tube like this, okay? And I could put ice up here. Here's water, and here's a piece of ice, right there, ice, right? Right? I could boil the water here and the ice won't melt. I could boil that water. Heat doesn't conduct, water doesn't conduct energy, water doesn't conduct heat very well. Frozen pipes. Why is it so difficult to get the water unfrozen from a pipe? Look, here's a pipe. And this goes into the ground. Can't see it. It goes into the ground, right? Here's my frozen solid water. Frozen solid, right? Frozen solid. So I have a pipe. Why is it so difficult? Now these are metal piping. Say they're metal, right? Why is it so difficult to unfreeze that? What conducts energy better, metal or water? Yeah. What happens when I heat this? the metal conducts the heat away. Conducts it away. This takes a long time to melt, that water. Water doesn't conduct energy well. Doesn't. What else is a very poor conductor of heat? What are the coals made of?
Coal?
No. Hot coals. What are they made of? CO. No, they're not made of coal. No, they're made of wood. They're wooden. It's charcoal.
Oh, charcoal.
Charcoal. They're wooden.
Really?
Yeah. Does wood conduct energy well? No. So what do you have to do? If you're going to walk on hot coals, what two things do you need?
Water.
Sweaty feet.
Really?
Yeah.
So,
What area of your body has a lot of pores? Your feet. A lot of pores, man. How many people hate sweaty feet? You get them all the time, right? Anybody live in cold environments? Yeah. Your body's warm, but your feet are cold. Isn't it? What's that about? Because your feet get so sweaty. So you walk on hot coals, you get sweaty feet walking on hot coals that are made of wood. They're wooden coals, charcoal. That's how it works. Because water is such a terrible conductor of heat, and so is wood. You get it? That's how it works. All right, we're almost done. Let's talk about shower curtains. Why does the shower curtain, think about it. Why does the shower curtain, how many people have a shower curtain in your shower? Raise your hand. Okay, don't you hate it when it blows in on you? Isn't that annoying? Okay,